In this video, we're going to introduce the ideal gas equation. So we've seen previously that 1 mole of any gas occupies 24 decimeter cubed under standard conditions of 25 degrees Celsius and 1 atmosphere pressure. But what happens if we increase the temperature of a gas? The particles will move faster because they will have more kinetic energy at a higher temperature. This means that they'll exert a greater force on the walls of the container, as they're going to collide with the walls of the container more often, and they're also going to collide with the walls of the container with greater energy. So this means that if we increase the temperature of a gas, the pressure will increase. If the gas is in a container which can't change its volume, so a container with rigid walls, then that will be the only thing that will happen. The pressure inside the container will increase. However, if you have a container which can expand, such as a balloon or a syringe, then it will do that as you increase the temperature. And that's because the pressure inside will suddenly be greater than the air pressure acting on the balloon or the syringe outside. And so therefore, the volume of that container will increase until you get to the same pressure. And the reason you will get to the same pressure is as that volume increases, that gives more space for the particles to move around, even though they're now at a higher temperature moving faster. And so eventually they will be colliding with the walls of the container less, and the pressure will get back to atmospheric pressure or whatever pressure is acting on the outside. So we've seen that temperature and pressure, and in some cases volume, are definitely linked, and the pressure and volume of a gas are also related. So if we take a container of gas at a given pressure and then decrease the volume, such as by pushing in the plunger on a syringe, the particles will get pushed closer together, and this means they're going to collide with the walls of the container more often, and they're going to exert more pressure on the walls of the container. This means that pressure and volume are inversely related, so if you decrease the volume, you will increase the pressure, so long as the number of particles and the temperature stay the same. We can link all of these concepts together in something called the ideal gas equation, and it is written in the form PV equals nRT. Pressure and volume are on the same side of the equation. Now this makes sense because they're inversely related. So if you decrease the volume, you will increase the pressure by the same factor, and vice versa. On the other side of the equation, N is equal to the number of moles. So that tells us how many particles there are. The more particles there are, the more pressure or the volume will increase, or maybe a little bit of both. Because we talked about if we increase pressure in something like a balloon, then it will expand and the volume will increase. And temperature is also on this side of the equation. Again, if we increase temperature, then we're going to affect pressure and or volume. R stands for a constant called the gas constant. And this is just something that we put in the equation to make the numbers and the units work. The units of the gas constant 8.31 joules per mole per Kelvin. And in this equation, this is one of the rare ones where you don't have to worry too much about where these units come from. If you go back over GCSE physics, you can see how basically energy that is measured in joules could actually be expressed as Newton meters, but you don't really have to know how to derive those units. It is, however, really important that you get the units of everything else in the ideal gas equation correct, otherwise you're going to get your answers wrong by possibly a factor of 1,000 or more. So all the numbers are in sort of standard, what we call SI units. So this means that pressure is measured in pascals. Quite often in questions we're actually given the data in kilopascals, so we have to convert it. Pascals, incidentally, is a Newton per meter squared. Volume is measured in meters cubed. So again, this is quite different to what we're used to measuring volume in chemistry, which is normally centimeters cubed and decimeters cubed. N is measured in moles, which is what we're used to measuring the number of particles in, and temperature must be measured in Kelvin. So we can't have degrees C in this equation because degrees C has a minus scale and we can't have a negative pressure or volume. So the most common use of the ideal gas equation is to calculate the number of moles. Let's have a look at this example to see how we rearrange the equation and also how we convert each of the units. So the first thing I'm going to do is write the ideal gas equation, PV equals nRT, and then let's just rearrange it. We want to find the number of moles, which is N, so N is going to equal to PV over RT. Okay, now we need to substitute everything in correct units. So first of all, let's look at pressure. Pressure is given us 207, that is kilopascals, and we want pressure in pascals. So we times it by 1,000 to get 207,000 pascals. Then we are going to multiply by the volume, and the volume needs to be in meters cubed, and at the moment it's in decimeters cubed. So we divide by 1,000 to get from decimeter cubed to meters cubed. If you're still stuck on your volume conversions, have a look at the video on units. So one thing, we can divide it by 1,000 and just write the answer, but we could just also write in the equation 8.98 and do times 10 to the minus 3, which is what we would get on our calculator anyway, but that's a way of dividing by 1,000. Now you may have noticed that I took my pressure in kilopascals and times it by 1,000 to get pascals, and I took my volume in decimeter cubed and divided by 1,000 to get meters cubed, which means that those two operations actually do cancel them out. So you could simply have done 207 times 8.98 without changing the units. I'd advise that you don't do that, however, because if you get into the habit of doing that and then a question gives you decimeter cubed and pascals, or it gives you kilopascals and centimeters cubed, for example, then you're going to get it wrong. So just be aware of the units all the time. Also, sometimes you do get working marks for substituting the correct values into the equation. The next thing is the gas constant, which needs no converting. We stick it right in as 8.31, and then temperature, the final thing that needs changing from degrees C to Kelvin. To do that, we're going to add 273 degrees to give me a temperature of 293. I put all of that into my calculator, so there's a number of ways you can do that and get it right. You can, most graphical calculators or normal scientific calculators will allow you to put it in the form we've shown there, with the line dividing the top and the bottom half of the equation. That's a good way to do it so you can see what you're doing. Alternatively, just put the top half in brackets, press divide and put the bottom half in brackets. We get an answer of 0.763 moles, and that's my final answer. Now just a point on self-checking with the ideal gas equation. So gases do change their volume with temperature and pressure, and they do it in a relatively predictable way. So temperature of 20 degrees is quite close to room temperature, whereas in kilopascals, 1 atmosphere is just about equal to 100 kilopascals of pressure. So in this question, I have got a gas that it is approximately room temperature, 20 degrees, and is roughly double atmospheric pressure. Now, why is that important? Well, it means I can do a really quick kind of check to see if my figure is in the correct ballpark. And what I mean by that is I can use my volume, molar volume of 24. So if 8.98 decimeter cubed of gas was measured at room temperature and pressure, then we would calculate moles by simply doing that over 24. And when I do that, I get a number of moles of 0.374. Well, that isn't anywhere close to my actual value, but it is approximately half. And the reason it's approximately half is because this gas in the question that I'm doing is being measured at double pressure. Double pressure would actually take up half the volume even if you had the same number of moles. So it's just one way that you can get the idea that maybe or certainly what it does do is make sure that you haven't forgotten to sort of divide by 1,000 somewhere or times by 1,000, because you'll soon see if you are a factor of 1,000 out in your answer. We're just going to finally talk about what we actually mean by an ideal gas, because this is called the ideal gas equation. In reality, no gases are completely ideal, but we can think about what makes a gas behave in this nice, predictable way in relation to temperature, pressure, and volume. So we do tend to think of gases made up of molecules which are just moving randomly, and they move in straight lines until they hit something and they change direction. That's pretty much true. For an ideal gas, we think about it behaving as just a rigid sphere, every molecule, which obviously molecules are not spherical, they have shapes. We also think of the collisions as being what we call perfectly elastic. What that means is every time the gas hits the container, there's no loss of kinetic energy during that collision, and there's no energy transfer whatsoever. All of it is transferred into changing the direction of the gas. We also think about the temperature of the gas being proportional to average kinetic energy. And then the last 2 points are really key. So one of the things that makes an ideal gas behave in a predictable way is that there are no or completely negligible intermolecular forces between the gas molecules. Now, this obviously is not true, because even the most ideal of gases, which would be helium, can become a liquid if you cool it down enough. So we also think about the volume occupied by molecules being entirely negligible, relevant to the volume of the container. So meaning that really we talked about most gases having huge spaces between them, so that the volume occupied by the molecule itself has no real impact, and the space is how much space the particles have to move around in. So when do these not work? That's the key thing that we might need to know. Well, the intermolecular forces thing becomes much less applicable at lower temperatures. So at lower temperatures, the slower the gas particles are moving, the more important the attractions between them become, and the more likely they are to actually get slowed down by other gas particles because they get attracted towards them. This also becomes really not applicable when a gas is near its boiling point. So when it's near its boiling point, it's near to condensing back into a liquid, which means the attractions between the molecules are quite significant. So the most ideal gases are the ones with the lowest boiling points. And the other point, the point about the volume occupied by the molecules, the more you compress your molecules together, the less the space between them gets. That becomes much less applicable, and therefore gases behave less like ideal gases at higher pressures. So if you want some more help with your A-level chemistry calculations, I've got a full online course, which actually this video was modified from. It's called Confidence in Chemistry Calculations. And at the moment, you can get that absolutely free for 2 weeks. Let me just show you what's in the course. So there are 8 different modules which look at the essentials, equation skills, relative atomic mass, formula mass, empirical molecular mass, percentage yield, atom economy, all these different things, titrations, loads of stuff on solutions, calculations, also Avogadro, and long answer problems. So there is some like really more challenging ones, and it comes with a full booklet of different chemistry calculations with full mark schemes and explanations as well. All of the more difficult questions that I put on there have video walkthroughs, so you don't just get a mark scheme, you actually get how to do it. Each one of these modules has like at least 6 different lessons in it, quizzes and ways to assess yourself. And actually you can access this course as part of my A-level revision memberships, which includes loads of other different topic videos and practice questions, and not just the calculations course. So the calculations course is included in the bronze, silver and gold membership. The only difference between the three of these is that with the silver membership, you get a full monthly assessment where you do an assessment exercise and I mark it for you, give you that examiner's perspective, give you personalized recorded feedback. And with the gold membership, there's just a few spaces left for my AQA and OCRA group chemistry lessons. Those are for year 13 because my year 12 course is full. But if you just wanted to try out the bronze membership, which is only £5 a month anyway, including the whole calculations course and 22 other different topics, along with practice questions and masterclass videos, that's actually available right now for a 2-week free trial. So you can try it, see how you get on, and if you can't even afford the £5 a month, you could sign up if you've got like a mock exam or a retake coming up. So go to my website, ckchemistry.co.uk. You'll also find loads of free revision downloads there as well. And of course, subscribe to my YouTube channel because I'm going to do at least 1 video a week and probably 2 for the next term or so.